Hello everyone, and welcome to the very first episode of Physics Friday, where we will be solving some fun and sometimes a little bit stupid physics problems. So for this first episode, this is actually a suggestion from the comments by Jude from the pineapple video, where basically he asked the probability that the pineapple that fell from the 100 and whatever foot tree quantum tunneled through the Earth. And I thought, that'd be fun to do, wouldn't it? So yeah, let's do that. So a few quick assumptions that we're going to be making is that we are within the tunneling regime, basically meaning that we can use the equation I'm about to write down, and also we're going to be assuming this is a point pineapple. Basically, this is going to be instead of having a bunch of different atoms or molecules in the pineapple, it's just going to be a singular particle, basically. A point pineapple. Has a nice ring to it. Alliteration. Anyway, going off of this first assumption, let's actually start some calculations, shall we? So based off of this, we know that T is going to be asymptotically proportional to e to the minus 2 lambda, where our lambda here is just going to be equal to 1 over h bar, which is Planck's reduced constant, times the integral from 0 to L of the absolute value of our momentum with respect to x. Now, we can actually simplify this quite a bit, thankfully. Basically, we know that our momentum is just going to be our square root of 2m times e minus our potential, v naught. I am assuming that's just going to be a constant potential throughout. And in fact, to simplify things the most, I'm going to be assuming that e is going to be much greater than v naught, basically such that we can write p as the square root of 2m times e. This is for a couple of reasons. First and foremost, it just simplifies the calculations, and second of all, it actually I'm actually pretty sure that we're moving from one side of the sphere to another, so I don't know if any work is actually done, but again, I'm a physics student, not exactly a professor. I'll have to look into that more. But for the sake of the fun of this video, we are just going to be assuming that. So, using this, we can actually simplify things quite a bit, because this is just going to be constant. So we can pull that out of the integral, which leaves us with gamma, being equal to 1 over h bar times L times the square root of 2m times e. And this is actually a pretty good time to actually start plugging in, or calculating, I should say, some values. So we know 1 over h bar, that is just a constant that we can just kind of look up. So let's start calculating L and also E. But first, let's just kind of get M out of the way. That actual average mass of a pineapple, M actually is just like 1 kilogram. If you actually Google it, some sources say, yeah, it's like half a kilogram, but I'm sure you could find a 2 kilogram pineapple if you look hard enough. So, I mean, we're just going to assume 1 kilogram for the sake of simplicity. So, at any rate, let's start solving for things. So, E, we're going to calculate the total energy of our pineapple. It's just going to be gravitational potential energy, because we're traveling through the Earth. So, it's going to be negative big G times the mass of the Earth times the mass of our pineapple, which is just 1, but I'll write it anyway, divided by r times the radius of the Earth. And plugging everything in, we actually end up getting negative 6.2 times 10 to the 7. Now, one caveat you might notice here is that, yeah, that is a negative, but at the end of the day, technically, this is an absolute value right here. So we're taking our absolute value of our momentum. So even though we might get an imaginary part, it really doesn't matter, because again, it's an absolute value where we care about magnitude, not necessarily the sign right here. So yes, for now on, I'm just going to drop that negative sign as a result. So now that we have that, let's calculate the slightly more interesting L. So our L is just going to be equal to the distance, basically. So imagine this is the Earth. Here's Austin from where I am, and I'm using Beijing as China in general, just from capital to capital for sake of simplicity. So we're basically concerned with the straight line distance between these 2 points. Now, whenever you go to Google it, you end up getting air travel distance, which makes sense, because I don't think many people are actually interested in how many like straight line kilometers or miles or whatever are between Austin and Beijing. I mean, it's not too relevant. Air is much more important, but we do need actual straight line distance this time. So we are going to be using some nice formulas. So basically, between 2 points on well, we should probably express these in terms of points as well. Let's do that first. So for Austin, in terms of this is going to be in terms of spherical coordinates. So our theta is going to be equal to 59.73 degrees. I'm going to call this theta 1. And our phi is going to be equal to, let's see, negative 97.73 degrees. Now, I would like just to point out that this is using the physics convention. So if I was to draw a sphere here, this angle right here is going to be theta, and this angle right here on like the xy plane is going to be phi. Just want to point that out. Now for Beijing. Really hope this spelling's right. We have our theta 2, which is equal to 50.1 degrees, and then we have our phi 2, which is going to be equal to, let's see, 116.4 degrees, which makes sense. Like heuristically, like they're on about opposite sides of the Earth, so it makes sense that like the difference between these two is, you know, quite a bit. And also, if you again look at a globe, it's like, yeah, well, these are like about the same, like they're like kind of about at the same latitude, I believe. So anyway, like heuristically or at first glance, these aren't like, these do make sense when you Google them. So using this and a nice formula, let's recalculate the distance between Austin and Beijing. The actual formula is just going to be 2r squared, where r is actually, you know, the radius of the Earth, of 1 minus sine theta 1 sine theta 2 times the cosine of phi 1 minus phi 2, or the other way around. Cosine is like symmetrical like that. We love that. Plus cos theta 1 cos theta 2. It's a very long formula. It's just distance in spherical coordinates, which isn't very nice. But at the end of the day, this does end up giving us about 10 to the 7 meters. So, with that calculated, which is quite cool, we now have essentially everything we need to actually find the probability that our pineapple does actually quantum tunnel to China. So, going up here, actually we'll go down here, or up here. I'm indecisive today. We have 1 over h bar times our L, which is just 10 to the 7, times our square root, which is just going to be 2 times 6.2 times 10 to the 7. Sorry, gamma, sorry. And this gamma is equal to, let's see, about 1.06 times 10 to the 45, which is a pretty big number, as you would expect. So we can represent this as e to the negative 2 times 1.06 times 10 to the 45. And this is the probability that our pineapple goes to China, but we can also make this a bit nicer. Like the way these probabilities are usually expressed, or like 10 to the 10 to the something. So we can actually simplify this quite a bit more, just change this to base 10. Basically giving us that the probability that the pineapple quantum tunnels to China is 10. 10 to the 9.21 times 10 to the 44. We're changing bases, that's why the power decreases. That should be negative right there. So the probability that the pineapple quantum tunnels to China is about, you know, given our assumptions, 10 to the negative 9.21 times 10 to the 44. If this happens, I will be buying multiple lottery tickets. So yeah, I hope you all enjoyed this video and this first episode of Physics Friday, and I'll see you all in the next one. Adios.